Yeah. Good. Okay, so if you didn't get your test back last day, you can come grab it. They're sorted alphabetically. If you don't have the chapter 4 notes from last day, does chapter 4? So I handed these out last day, so if you were here, if you weren't here, busted, come grab it. It's okay. I also have lots of other notes here. I have the chapter 2 notes, I have the 3.4 notes, I have the chapter 3 notes. All these papers. Okay. So we're going to keep working in the chapter 4 notes. It was a while ago, so I'll do a little bit of a review. Okay. And then we'll keep talking about hypothesis testing. Okay. So, all right. This is from last day. Seems like ages ago. What? Seems like just yesterday. Yeah, maybe. Then you didn't do your break right. Okay, so we started talking about inference. Inference is when we take sample information to try to know something about the population. And so there's a couple of different ways that we can do that. The main ones being hypothesis testing and confidence intervals. And so we just started talking about hypothesis testing, but to get there, what we had to talk about was, okay, well, before we've just been talking about how one observation is distributed, right? So a single observation follows a normal distribution with a mean mu and a standard deviation sigma, fine. But then we said, okay, well, if we collect a sample, right, of size n, then we can talk about how the mean is distributed, how the sample mean is distributed. So the sample mean follows a normal distribution as well. Okay. It's centered on the same mean as the single observations. That makes sense, right? Average should be hovering around the average, right? The only thing that changes is the spread. The spread gets tighter and tighter as you increase your sample size. Right? And so we have this kind of the standard deviation of sigma over root n, which gets confusing. So sigma over root n is actually just called the standard error instead of standard deviation. So the standard error is the spread for your sample mean. So we did some examples looking at that, did lots of examples actually. And then we said, okay, that's all fine, knowing how the mean is distributed, right? But what we're really interested in is probabilities associated with the mean. Right? And so to get to those probabilities, we use z-scores still, right? We just alter our z-score formula slightly, so z is still a z. We know how to deal with z's. You had to do that on the test. But now we replace our x with x bar and see how far it is from the mean. This is now the mean of x bar, right? But it's the same as for a single observation. And then instead of just dividing by sigma, now we're dividing by sigma over root n. And so once you have your z-score, then everything is the same, right? You use your z-table to find the probability that you need. Probabilities, in case it's been a while, right, are areas under the curve. Right? And so we're always pushing to find these areas under the curve, or vice versa, right, where we have an area under the curve and we want to find what value makes that happen. Okay? So we did this example, the weight of the boxes. And then we talked about the central limit theorem, which is just as important as it sounds, central limit theorem. But it's not that revolutionary because all it says is that, okay, it actually doesn't matter where you're pulling your information from, right? Where you're pulling your sample from, as long as you have a large enough sample size, the mean will follow a normal distribution. So that's kind of cool. So within reason, the mean will always follow a normal distribution. So you don't have to pull from a normal distribution. And we did this example, which we obviously don't have time to redo, but I do suggest you kind of skimming it over maybe later. Okay. But we'll do more work with it, so don't worry. So I showed you this where, okay, if we pull a sample from this very skewed distribution, skewed because I think I have 1,000 or 10,000 points in there, I can't remember, right? But eventually, as you collect a larger and larger sample, the mean tends towards the population mean, and so it stabilizes. Any questions so far? No. So then we started talking about hypothesis testing. And so the thing with hypothesis testing is that there's a lot of ins and outs and a lot of rules to remember and a lot of things to navigate. Okay? And so what I find works best is if I just walk you through all those rules, then we'll do an example just to kind of tie all those rules together. Right? And so it's going to feel kind of discombobulated for a little bit while we walk through all these rules and establish all these rules of the road, I guess. And then once we do the example, you'll see that a lot of it is going to feel familiar. It's just the formalization of it that's going to be a little bit different. Okay. So hypothesis testing is whenever you have some hypothesis, you have some idea or some inkling, right, that you want to prove or disprove. Right? For example, you've developed this painkiller and you want to show that yours acts significantly faster than all the other painkillers, for example. Right? You have to have some measurements. So you would do that using a hypothesis test. Right? So hypothesis testing is really, really important in any field. Okay? Whenever you want to prove something, you have to do a hypothesis test. Okay? So what we said, I don't expect you to remember it all. I'm kind of starting fresh here-ish. How about fresh? So there's 4 steps that we're going to follow for hypothesis testing. Okay? And what you'll notice is from now on, throughout the course, until the very last chapter, which is the fun chapter, fitting a line of best fit, kind of this fun end on a high note thing. But until then, what we're going to be doing is we're going to introduce all these different scenarios where we do hypothesis testing and then we develop confidence intervals. It just depends on what kind of data do you have, right? Because there's different ways that data can be collected, different ways that data can be related to each other, right? And so, for example, how you look at how one group behaves is different from comparing the means of 2 groups, for example, right? And so here we're laying the groundwork, but the steps for hypothesis testing are always the same, right? So we're always going to follow these 4 steps, and the rules that we establish here are always going to be the same, and so kind of a hefty section. So the first step is to state your null and alternative hypothesis. Okay? You start here to say, okay, well, here's what I believe, right? And if that's not true, then here's the other option. Right? Thinking back to, I don't know what science it is, presumably elementary school, I don't know. But you have this hypothesis that if you boil water, it'll turn into gas. Will it, won't it? I don't know. Right. But you have to say, okay, well, If that's not true, then it won't turn into gas, right? Or if it's true, then it will turn into gas, right? Same type of situation. So you state your null and alternative hypothesis, and then you do the test. I call this do the test, do the do. You actually know how to do the test already, because doing the test is just calculating a z-score, right? A z-score tells you how far is this observed mean from the hypothesized mean, right? It's just, we're putting it into this context now. Okay? So doing the test is going to be some calculation, so a z-score, and pretty quickly here we'll move into t-scores instead, and then for proportions we'll move back to z-scores, right? So there's only two options, z's and t's, at least for this course. Okay. Once you have your z-score, right, you're going to find the p-value. So find the p-value, even though we haven't called it a p-value before, the p-value is just the area in the tail. Okay? And we'll talk about what the p-value is, but it's typically just the area in the tail, okay? Which you know how to do, right? And so you've been doing step 2 and 3 already, right? Test 1, you've done it on assignment, so, or an assignment, I think. Yeah, so far. But steps 2 and 3, you know how to do. Okay? It's just introducing this kind of sandwich, step 1 and then step 4, right? Using this information to draw your conclusion. Okay? And so those are your 4 steps. Okay? And those are really vague because they apply to any sort of hypothesis testing that we're going to do. Any questions? Okay. So we started talking about the nitty-gritty of stating the null and the alternative hypothesis, but let's just get into that here. Oh, it's because I charged it. I'll just put February 25th there. Pretend we started there. Okay. So your null and alternative hypothesis is always going to be about the parameter. Remember, the parameter is a measurement from the population P and P, right? And the statistic is a measurement from the sample, right? And so I've already highlighted it here, but it's in terms of the parameter, and that's going to be really important. You don't want to know anything about your sample. You know everything about your sample, right? Your hypothesis is going to be about how the whole population behaves. And so it's going to have this type of setup. Okay? You're going to have your H naught, which I've got notes about it here, but H sub 0, H null, the null hypothesis. But I typically just call it H naught, which H-T, I guess. I had to look it up. I just think H-N-O-T, but it's not. Here's your null hypothesis. Here's your alternative hypothesis, HA, alternative, of course. And because these are statements, right? Here's my null hypothesis, blah. Here's my alternative hypothesis, blah. We follow up with colons. Okay? I see a lot of equal signs here, and I'm not going to deduct marks, but just keep in mind, I think it helps if you keep this in mind that it's a statement, so you're going to have colons here. We're going to start in the simplest case where we've collected one sample, right? And so we only have one sample mean that we could hypothesize anything about. Okay? What we're later going to do is we're going to collect 2 samples, compare those means, right? And so here's where we start with just one sample, how does that sample mean compare to some hypothesized value? Okay. And so because we have to talk about the parameter for a mean is mu, right? And so for one sample mean, it's going to be about mu. Okay. Your null hypothesis has to have an equal sign in it. Okay. The reason for that is you have to say, okay, well, these two things are the same until I have proof otherwise. Okay. And so your null hypothesis always has an equal sign in it. The value that's going to change, depending on the question, is mu naught. Okay? Mu naught is the value that you want to compare your sample mean to. Okay? And because I've taught this a lot, pretty sure all of these points are just outlined below. Put them on, but pretty sure. Okay? So, that's kind of a tricky part for a lot of people when we start doing this is, okay, we're going to have some sample information, so a sample mean, but then there's going to be a value that we want to compare that mean to, right? That value, this kind of picked value, is your mu naught. And then your alternative hypothesis is going to be about the same thing. So if you have a mu here, you have a mu here. Right? And if you have a mu naught here, you have a mu naught here. The only thing that changes is the sign in the alternative hypothesis. And I'll make a note of that. What the? It was working. Come on. Oh, just a little sluggish. The only thing that changes, I'm gonna not have very much room here. The only thing that changes is the sign in HA. Make this smaller. The only thing that changes besides the sign here, in the alternative hypothesis, everything else stays the same, right? Except this is your null and this is your alternative hypothesis. And so that's important to keep in mind too, right? That you have the same thing going on up top that you have on the bottom, just changing the sign. Right? They can't be equal to anymore. Yeah. The default is going to be not equal to, right? Either, so you're saying either two things are equal or they're not equal to each other. Right? Depending on the question, okay, you could have less than or greater than, right? And I don't know about you guys, but I have a hard time with inequalities, and for some reason, I was always doing the gator. The alligator eats the bigger one. But then it was actually not until I was teaching that someone was like, well, you just make an L and then it's less than. So, pretty helpful. Anyways, so the L is the less than, because then you can just read it, right? Mu less than, mu not. You learned so much. Anyways, so you're good with inequalities, then good for you. I was not. So we've got three options, less than, greater than, or just not equal to. Okay. The thing with these two is that you're only concerned with one extreme, right? Either something is significantly less than some hypothesized number, right? Putting it down on the lower tail, right? Thinking about our normal distribution, which we're going to tie in, right? Or greater than, right? Then your sample mean is significantly above your hypothesized mean. So here, you're only concerned with one of the tails, sorry. Right, and so we call this a one-sided or a one-tailed test. Here, the not equal to, you don't care which direction it's going in, right? As long as it's significantly different, right, then you've got a result. And so here, these two, what the? It keeps not wanting to do anything, which is not helpful. Bling. So these two are called one-sided. I don't know what's so popular today. Or one-tailed tests. Test because we're doing a hypothesis test, right? And if you have a less than or a greater than, then you have a one-sided or a one-tailed test. I'll call it one-sided, just that's what I like to call it. But if you want to call it one-tailed, I'll know what you mean. You should know that they're the same. Right? And then here, this is a two-sided or, of course, two-tailed test. Why is this important? Why is it important to know if we have a one-sided or a two-sided test? Because later on in step 3, when we find the p-value, we have to know which area in the tail we have to find. Okay. And so what we're going to end up having is a one-sided or a two-sided p-value, and that's going to hinge on your alternative hypothesis. And so I'll make a little note here. We need to know if we have a 1 or two-sided test, for our p-value in step 3. One of the main questions that I get, unfortunately, very close to final exam time is, how do I know if I have a one or a two-sided test? How on earth am I supposed to know that? Not like that, but in my mind, that's what it says. So then I'll say, well, it depends on your alternative hypothesis, right? So even though we're talking about the p-value, which remember is all the way down in step 3, here you have to look back to your first step, your alternative hypothesis, and say, okay, well, if I only care about one side, I have a one-sided test. If I care about two sides, I have a two-sided test. And it's okay, you'll forget it, but maybe some of you won't. Oh, look, we're only concerned with one extreme, have a less than or greater than. In our alternative hypothesis, we have a one-sided or one-tailed test. Hey, that's exactly what I said. If we want to detect a difference, we have a two-sided or a two-tailed test. Okay. I'd say that this is all, these are all the ins and outs of step one, stating your null and alternative hypothesis. Okay. Any questions about it? Hard without an example. You'll have questions once we do the example, I think. Okay. But for now, we're just running through the lay of the land here. Step two, do the test, do the do. Doing the test means we calculate how far is our sample mean from our hypothesized mean, right? Mu naught is your hypothesized mean, taking into account sigma and the sample size. Later on, we're going to calculate t-scores instead. If you do a compare and contrast here, you'll notice that the only difference between t and z is here you've got sigma and here you've got s. Remember, s is your sample standard deviation. Sigma is your population standard deviation. Right? Here, we're pretending to know the population standard deviation, which I'll get into later, but it doesn't really make sense. Right? And so in practice, what we're going to do, we're just going to calculate t-scores. Right? But for this course, I have to teach you how to use set scores, and they're good. They're kind of like training wheels. Okay? But out in the field, you'll only calculate t-scores or t-tests is what we call them. You might have even if you've read articles and things like that, right? We did a t-test and we found this. So that's what it is. Yeah. But it's very similar, right? The only difference is that here you have sigma and here you have the sample standard deviation instead. Remember what the z-score is, right? Always kind of keep that in mind. Right, the z-score and the t-score later on just tell us how far your sample mean is from your hypothesized mean, taking into account the spread, right? The spread that you're expecting to see. Okay. And because you've already done this, there's not really notes about it. Step two is pretty quick and dirty. You just do a calculation and then you move on to step three. One thing to keep in mind is that the Z or the T that we find is going to be called a test statistic. Okay? And so if you see that, right, what is the test statistic? It's hard to say, that's for one. That's for sure, but it's just called a test statistic. So from there, we'll move on to step three then. Step three is where we find the p-value. The p-value, we've already kind of hinted at, is the area in the tail. But by definition, so the formal definition is of a p-value is the probability. The probability, remember, is the area in the under the curve. The probability of observing something x bar in this case, right? One sample mean in this case, as extreme or more extreme than what you observed. And so that's what makes it the area in the tail, right? As extreme or more extreme. Okay? Whether you're on the lower tail or the upper tail, right? As extreme or more extreme just puts you further out into the tails. Okay? And so I say it's pretty much a rule. So in most instances, the p-value will be the area in the tail. Okay? You do have to keep your wits about you because you don't want to be testing something that doesn't make sense, right? You can't use a value of 10 to prove that it's greater than 15. Right? I think we all understand that, right? But I've seen that happen a lot, actually, is where you have a value that's less than something, but you want to prove that it's greater than something, and it just doesn't jive, right? And so if you've set up your hypotheses correctly, then it's not a problem, right? Then the p-value will just be the area in the tail. The second point might be the most useful in trying to figure out what the p-value is. The p-value is going to become this thing that you know you're supposed to know about, but it's like a weird thing. Okay? I do have the caveat that it's not completely accurate, and that's just me being really, really picky. Okay? You can think of the p-value as the probability that the null hypothesis is true. Okay? So if you think of it that way, right, the probability that the null hypothesis is true, then how we draw our conclusion is going to make a lot more sense. For example, if the p-value, right, the probability that the null hypothesis is true is very, very small, then H0 is probably not true, and you should go for HA instead. So that's where we're headed. Like I said earlier, the p-value depends on the sign in the alternative hypothesis, specifically whether we have a one or a two-sided test. Okay. What we do for a one-sided test is we just find the area in the tail, and that's it. That's your p-value. Okay. For two-sided tests, right, gets a little trickier because we only have one sample. Right? So our sample mean is either going to be below or above the hypothesized mean. Right? It's just, that's how it is. Okay? But what we do is we find the area in the tail, and then we multiply it by 2 and pretend that it happened on the other side as well. Okay? And so just to illustrate, if here I have equals, that's wrong. Okay. So let me zoom in here. I'll even, oh, this silly pen. I think it needs a charge. I was going to change it to colon. It doesn't matter. Okay. So your one-sided p-value, say you have an x. So you found a value, right? Here's your hypothesized mean. Here's your value that you found, your sample mean. It's 2 standard deviations below the hypothesized mean, right? Then here, this area in the tail is your one-sided p-value. That's if you want to know if mu is less than the hypothesized mean. Okay. Same thing if you want to know if mu is greater than the hypothesized mean. So your hypothesized mean is here, and you have a sample mean that's above it. Then, and it's 2 standard deviations above it, let's say, then the area in the tail is your p-value, your one-sided p-value. Same idea here, right? Like I said, you're only going to find a sample mean on one of these tails, right? But if you need a two-sided p-value, you're going to find the area in the tail here, and then double it and pretend it happened down here as well. You're just saying, is it different from this value in the middle? Okay. Any questions with those? Step 4, finally, is our conclusion. The conclusion's a big deal, right? The conclusion is the reason we're doing all this testing, right? Your conclusion is basically going to be your entire research paper, right? Here's what we found. It was significantly different from this value. Here's why, right? And so your conclusion is really, really important. We use our p-value, the probability that the null hypothesis is true, let's think about it that way, to draw our conclusion about our hypothesis. And so, as a rule, if the p-value is small enough, and we'll talk about how small is small, right? But if the p-value is small enough, then we say that we have enough evidence to reject the null hypothesis in favor of the alternative hypothesis. And that's where it's helpful to think of the p-value, right, as the probability that the null hypothesis is true, because if it's small enough, then you can reject the null hypothesis and conclude the alternative hypothesis. So how do we know if it's small enough? It depends on the test. But what we're going to do is we're going to have some alpha level, right? Alpha is the Greek fish symbol. So we have some alpha level that we're going to compare our p-value to. Right? This is where kind of things derail. There's p-values, there's alpha levels, there's one-sided, two-sided, but you'll get there. Okay? So to determine if the p-value is small enough, okay, we compare it to the alpha level. And so we have to have some threshold that says, okay, anything smaller than this will be considered small enough. Okay? As a default, we're going to use 0.05 as our alpha level. I don't have that on here, I guess. Oh, yes, I do. The default alpha level is 0.05. So, what we say is that if the p-value is less than the alpha level, okay, I know that's all jargon, we have enough evidence to reject H0 in favor of HA. Like I said, the default alpha level is 0.05. Okay. On a test, of course, I would just tell you, use an alpha level of whatever, if I don't want you to use 0.05. Okay. An example of where you might want to alter it, so most fields use 0.05 and that's fine. For medicine, for example, you might want to be more certain of your results, so you lower your p-value or your alpha level, right? You have to get a really, really small alpha level because it has to be safe and all that kind of fun stuff, right? But for run-of-the-mill testing, we use 0.05, and that's kind of good across the board, right? But if it's really important, you lower the alpha level, 0.01, 0.001 if you want to be really, really sure. Right? Just depends. And if you don't really care, 0.1, you can use an alpha level 0.1 sometimes. Okay. So here, right, we're comparing the p-value to the alpha level. Right? So depending on how the p-value compares, right, the p-value can either be less than the alpha level or not less than the alpha level. Notice that I'm just using the, I don't know what the grammatical term is, but I'm just saying it's less than or it's not less than, right? And that's going to help you kind of structure your sentence, because then you only need to make minor tweaks, right? So I wouldn't say it's greater than, I would just say it's either less than the alpha level, right? Which means you can reject your null hypothesis, or it's not less than the alpha level, which means you cannot reject your null hypothesis. Okay? So here, if the p-value is less than the alpha level, we have enough evidence to reject H0 in favor of HA. If the p-value is not less than the alpha level, we do not have enough evidence to reject the null hypothesis. And so these two are going to be really important. See if my pen's behaving. Seems to be. I want you to highlight those or do something because those are really, really important. Notice that we're drawing our conclusion in terms of, well, can we reject H naught or can we not reject H naught, right? Which is it? So we only state our conclusion in terms of the null hypothesis. And the reason for that is because we've done all our testing assuming that the null hypothesis is true, right? If you think about your hypothesis, right? The null hypothesis in general is that mu is equal to mu naught. Right? So now if we do all our testing assuming that mu is equal to mu naught, then that's what we used in our z-score here, right? We said, well, okay, assuming mu is equal to mu naught. Right? So we've done all our testing assuming that the null hypothesis is true. So that's why our conclusion has to be in terms of H naught. Okay? So it's important that we state our conclusion in terms of H naught since we've done all of our testing, assuming H naught is true. Okay? So once we have our conclusion in terms of, okay, can we reject H naught or can we not reject H naught? Then we can actually answer the question, right? We can translate that into an answer for the specific question that we were asking. And what I would do is I would just reformulate the question as an answer. Yes, there is evidence, or no, there is not evidence. Typically, these questions will start with, is there evidence that this and this and this? Right? Yes, there is evidence, or no, there is not. Okay? So just to reiterate, your conclusion is going to have three parts. Okay. First thing you're going to do is take your p-value from the previous step, compare it to the alpha level. Right. How does it compare? Is it less than the alpha level or is it not less than the alpha level? Then you're going to draw your conclusion in terms of the null hypothesis. If the alpha, or if the p-value is less than the alpha level, have enough evidence to reject H naught. On the other hand, if the p-value is not less than the alpha level, you do not have enough evidence to reject H naught. And then what does that mean in terms of the actual question? I think people get so caught up in following all these steps and doing all these things that this one is forgotten, even though it's the easiest, right? You've done all the work. Now you can just answer the question, right? But step 3 is the one that's forgotten most often. Okay. And then I'm pretty proud of this one. I use it every year, every term even. But also because I think it's really helpful, right? Because we have to remember, right? Okay, so if the p-value is small enough, right, then the null hypothesis, you can reject the null hypothesis. If the p is low, then the null hypothesis must go. Has a nice ring to it. All right. Do you feel inundated with information? Probably. Let's do an example just to see what's going on. See if we have a handle on this stuff. It's actually hard to find good questions where we know sigma. Okay. And so we're not going to spend a lot of time in this section, but we use it just to introduce all these ideas. Okay. So we're going to talk about odor thresholds. So example 3. So if we measure the DMS odor thresholds, doesn't matter what it is, but it gives an off odor in wine. That's important. Okay. Of individual adults, the values follow the normal distribution with a mean of 25 micrograms per liter and a standard deviation of 7 micrograms per liter. Units don't matter. Okay. And so here, you can see why this would be important. So you're producing wine, there's always going to be this kind of DMS in your wine, right? But you want to have it so that it's not detectable, right, by our noses. Trained noses might be able to detect it. But for us, or at least myself, run-of-the-mill, whatever's, we probably won't be able to detect anything. Okay. And so here we're told that for individual adults, right, the odor thresholds have a mean of 25, whatever, units, and a standard deviation of 7. So what we're told here is essentially that X, right, an individual adult, follows a normal distribution with a mean of 25 and a standard deviation sigma, or 7, sorry. Individual adults. We would like to know if wine tasters, right, presumably they have a more trained nose, right? We would like to know if wine tasters have a lower odor threshold than the general population, right? So here's the general population. So individual adults, I'll put in brackets, general population. Oh. So we have this hypothesis, right? We suspect that wine tasters are going to have a lower odor threshold than the general population, but we don't know, right? So we have to prove it for our hands. So we suspect that they do, but we collect a random sample of odor thresholds for 30 wine tasters so that we can confirm our theory. Okay. And so here again, we've got these wine tasters making up our sample. So we find that their mean odor threshold is 21.5. 21.5, that's your sample mean. Oops. We know that 21.5, right, compared to 25, 21.5 is less than 25, right? That's a fact. 21.5 is less than 25. What we want to know is it significantly less than 25, right? And that's the whole goal of hypothesis testing, right? So you found this value, 21.5. It's less than 25, but we would need to know, is it significantly less than 25? Do a little arrow here. 21.5 is less than 25, but we want to know if it is significantly, underline that, less than 25. So we've got a sample mean, right, 21.5, that we want to compare to 25. So now when we go and we set up our null and alternative hypothesis, we're going to have something like H naught HA. We can start there. We have a sample mean, so we want to be able to talk about the population mean, right? How does the population mean compared to 25? So mu, whatever value you have here has to go here, right? You have to talk about the same thing in both of your statements. So you can start there. Just kind of use the same value there and there. Okay. Another rule that we established was that the null hypothesis always has an equal sign in it. Right? And so you can throw that in there. Sometimes if I don't know where to start, I just start with the equal sign and then just kind of work my way out. Right? And so now you've got mu equals, and we have to put some value here. Right? And so we want to know if it's significantly less than 25, right? 25 is just the value that we want to compare our sample mean to, right? And so we want to put 25 here. Okay. It's important that you don't put your sample mean in your hypothesis. You know exactly what your sample looks like, right? So it stays out of the null and alternative hypothesis. You want to talk about the value that you want to compare your sample means to. Okay? And whatever value you have here, you have to talk about down here. Remember, the only difference is the sign in the alternative. Okay? I guess I've given it to you already in the typed up version, but not that strange to think that, okay, well, we want to know if it's significantly less than 25, right? And so from the question, we know that the sign in the alternative hypothesis should be less than. So less than. What I'm going to do is, because here, right, because I only care about one extreme, right, is 21.5 significantly less than 25? I have a one-sided test. So what I encourage you to get in the habit of doing is just in brackets put one-sided test. Oops. Just so when you look back, right, but here it's fresh, right? And then you can remind yourself later on. I'll clean up this lesson. Okay. So just a reminder, right now we have a one-sided test. So there's your null and alternative hypothesis. Okay. We do all our testing assuming that the null hypothesis is true. The null hypothesis says that, well, mu is equal to 25. So now when we do all our testing, we assume mu is 25. And then at the end, we'll see if that's reasonable or not. Okay. Any questions about that step? No? Okay. So step 2, do the test. We have to calculate a z-score. Got some mumbo jumbo here, right? But if we calculate our z-score, alongside here, z is x bar minus mu naught over sigma over root n. Our x bar, our sample mean, is 21.5. How far is it from our hypothesized mean of 25? Over sigma, which is 7, over the square root of n, which is 30. (21.5 minus 25). Negative 3.57 divided by 1.278019301. So I get roughly negative 2.74, right, to 2 decimal places. So now back to Z's, you know that Z scores have to have 2 decimal places, right, because that's what the Z table has. So you can't have any less and you can't have any more. I've also got the calculation here, right? So you wanted to check it, but just showing you what we would do. Because I talk a lot in this section, it seems. As a rule, right, we said that any Z score more than 2, right, in either direction will be considered extreme. Right, so just as a check-in point, because we have a Z score of negative 2.74, we already suspect that we're going to be rejecting the null hypothesis, right? Because the null hypothesis says that the mean is 25, but here we're finding that's a little far away compared to our sample mean, right? And so already we have this idea of, okay, well, it looks like I'm going to be rejecting the null hypothesis. Right? The p-value just formalizes that idea, right? The p-value just attaches a probability to that idea. Oh, I have a little side note here. What if the mean of our sample was 23? Just to get an idea of how these things move around. So do a different color here. Z is x bar minus mu naught. Just for a second. And also because I can't remember if it changed or not. 23, well, it changed, but 23 minus 25 over 7 over the square root of 30. I get negative 1.564921.593, but my calculator is a little crappy, so assuming you get the same thing. Right, so, and probably why I picked 23. Here, if our sample mean wasn't 21.5, it was 23. 23 is also less than 25. Right, but just looking at these values, we're not going to keep going with this one, but just to show what's going on, right, just looking at this, it looks like it's not that far away from 25, right, so we wouldn't probably reject the null hypothesis here. We would have to go through and do the rest of the steps to find out, but here, right, because we're so far away from the hypothesized mean, then we'll probably end up rejecting the null hypothesis. So you can get a pretty good idea of what's going to happen just by your Z score. Right. Step 3, find the p-value. Okay. You have your Z table, right? Your p-value is going to be, change the color here. We can draw out our normal distribution. It's going to be centered on the hypothesized mean, 25. We have a mean of 21.5. And so this area here, this is our one-sided p-value. Right? The p-value is the probability, so the area under the curve, the probability of something as extreme or more extreme than what you saw in your sample. So all we have to do now is we have to say, okay, well, we have a z of negative 2.74. We can use our z table to find the area to the left. Right? Of course, if we had to find the area up above here, you'd have to use that 1 minus trick. Right? No big deal. We're kind of well versed in that now. Right? And so here, from our z table, we find the area to the left of z equal to negative 2.74 is 0.0031. This will be our p-value. In fact, I'll just add that it's our one-sided p-value is 0.0031. So now we have our p-value. Not that bad. It's just mapping it out, seeing which area you need. It's going to be an area in the tail. So now it's time for our conclusion. Remember, our conclusion has 3 steps. Right? First thing we have to do is we have to compare our p-value to the alpha level. If I don't give you an alpha level saying use an alpha level of whatever, just use 0.05. Right? That's the default. So here, our conclusion, since our p-value is 0.0031, it's less than our assumed alpha level of 0.05. I like to throw that in. If I'm assuming that the alpha level is 0.05, I like to just say that, hey, here's an assumption that I'm making. Which means we have enough evidence to reject H0 in favor of HA. And so this statement is exactly what I'm expecting to see. And you can just reword that. So you compare your p-value to the alpha level. Right? Is it less than or is it not less than the alpha level? And then what does that mean? Can you reject the null hypothesis or can you not reject the null hypothesis? And then here, the last part of our conclusion, because I've gotten a little wordy there in the middle, is this last statement. That means, so what does it mean? So we've decided, okay, our p-value of 0.0031 is less than our alpha level, right? It's less than 0.05, okay? Which means we have enough evidence to reject H0 in favor of HA. Remember, our H0 was that mu is 25. We're rejecting that and saying, no, it's more likely that mu is less than 25, which is your alternative hypothesis. So in terms of the question, that means that we can conclude that wine tasters have a significantly lower odor threshold than the general population. Some talking in between. But so a lot of steps, right? But once you get in the habit of following these steps, it'll be a lot better. Right? Any questions? No? Okay. wish I had another example, but I don't on hand. So I guess we'll talk about confidence intervals. Covered a lot of ground today. Wasn't really expecting that. I'm not sure I want to get into confidence intervals quite yet. How about we just call it quits? Yeah? Okay, great. See you guys on Wednesday. Or maybe in the lab later, I don't know.